So what I'm going to try to do now is map between the natural numbers and the functions. So over here I'll have the natural numbers, n0. So let's put the natural numbers down, 0, 1, 2, 3, 4, 5, and so on. And over here, I'm going to put the functions. Now, if you remember, the way that we specify a function is that we specify it as a list of pairs from inputs to outputs. So I'll call my first function f0 of n. These are the functions that map a natural number onto a natural number. So the function that maps each number onto twice itself. You know, so 0 maps onto 0, 1 maps onto 2, 2 maps onto 4, 3 maps onto 6, and so on and so on. That's a function. Well, let's have that as our first function. f0 of n is going to be, well, let's remember, functions are specified as a set of pairs. So the first pair is going to be what 0 maps onto. So we know for this one, 0 maps onto 0. 1 will map onto 2. 2 will map onto 4. 3 will map onto 6. 4 will map onto 8. And so on and so on and so on, all the way up to infinity. So there's our first function. We've captured that one. So we're going to allow that function, we've numbered it 0. We've actually been cheeky enough and we've given it a little subscript 0 to say that's the function that I've mapped against 0 in my set of the natural numbers. And what I'm going to try to do is I'm going to, for each natural number, I'm going to try to write a function and show that I've captured them all. A bit like Pokemon, but very hard to catch Pokemon one. So let's have f1. Just needs to be another function. Well, one of the most well-known functions is called the identity. And the identity function simply maps its input directly to its output. So whatever you give it as input, that's the output. So 1 maps onto 1, 2 maps onto 2, 3 maps onto 3, 4 maps onto 4, and so on and so forth. Okay, you notice that these two functions, they agree on the output for 0. So if you put 0 into this function, you get 0 out. And if you put 0 into this function, you get 0 out. But these two functions disagree on what the output should be for 1. And that means no matter what goes on up here, these are different functions. If they disagree on one output, could be more than one, if they disagree on one output, they're different functions. I'll illustrate this with the next function. What I'm going to do is I'm going to let it be a function that maps 0 onto 1, but otherwise it's the same as the identity function. So it maps 2 onto 2, 3 onto 3, 4 onto 4, and so on. So because these two functions differ on what should come out when you put 0 in, that means they're different functions. If that was a 0 and everything else was the same, they'd be the same function. But because there was a different value here, f2 is not the same as f1. They're different. You might think I'm labouring that point, but in fact that's going to be really important in a minute. Let's have another function. Let's map everything onto 0. Why not? So this is this is a function, and you're allowed to do this. Perfectly decent function. Every time you get an input, it just maps that input on straight onto 0. Everything goes to 0. Certainly not a very interesting function, but it is a function. Let's have another function, f4. We talked about the squared function earlier. Well, let's have that one. 0 maps onto 0. 1 maps onto 1. 2 maps onto 4. Now you notice that so far, actually it's different there. So this function is different from this one because they differ there. But they've got the same outputs here and here, but here it's different. So 3, what we're doing, squared, and then 4 will map onto 16. So far, I've only done computable functions. So this is the doubling function. This is the identity function. This is the identity function, except that this value is 1 rather than 0. Everything maps to 0. That's an easy one. Just return 0 will do it. This is the squared function. Let's do a function that looks a little bit more haphazard. So let's say that 0 maps onto 9. 1 maps onto 25. 2 maps onto 0. 3 maps onto 3. And 4 maps onto 512, for example. So this is an example of a function where it doesn't look desperately computable. So it looks like, oh, how am I going to calculate these values? This is to give you the idea that there might be such things. But what I do know is that if I can map each and every function here onto a number here, and I know that numbers align to computer programs, I know that I'll have a computer program that sorts this out for me. So that's the hope. The problem is dear old Cantor. Along comes Cantor and spoils the show again with his diagonalization argument. With the diagonalization argument, it's going to apply in a very similar way to the way that it did when we tried to map the dog names on Zog, the real numbers, to the integers, or the natural numbers. Okay, so what we're going to do now is we are going to take the diagonal here. This is going to be the outputs from each of these functions. So the output here, the output here, the output here. So basically, if we look at F0 and look at the output for 0, currently it's 0. Look at F1 and look at the output for 1, it's 1. Look at F2 and look at the output for 2, it's 2. F3, look at the output for 3, it's 0. Look at F4, the output for 4 is 16. And so on and so on. So I didn't list the fifth one here, but we would, whatever the output for 5 would be for that one, you just keep going on forever. What we're now going to do is we're going to create Cantor's function. Cantor's function is going to be called f dash of n. And I haven't given f dash of n a number because it's going to turn out that it's impossible for f dash of n to have a number. And the way that we create Cantor's function is like this. For 0, what we do is we look at the output that f0 gives for 0 and we add 1 to it. So in other words, if the output for 0 is 0, for f dash, it's going to be 1. Doesn't really matter what it is, as long as it's different, and adding 1 to it will do us just fine. Let's look at what f dash has as the output for 1. the way that we do that is we look at the output for 1 from F1 and we add 1 to it. For the output for 2 for F dash, we look at this value and we add 1 to it. For the output for 3 from F dash, we look at the output for 3 from F3 and we add 1 to it. And for the output for 4 for F dash, we look up in our table here what the output for 4 is for F4 and we add 1 to it. Now what do we know about this function here, Cantor's function? F dash is certainly not the same as F0. Why? Well, they differ. And I did tell you that if two functions differ on an output, they're different functions. F dash similarly cannot be the same as F1. Why not? They differ on a value. F dash cannot be the same as F2. Why not? They differ on a value, and so on and so on and so on. So what that tells you is that F dash of n is a function which does not align to any of these numbers, but we've got all the numbers, we've got all the natural numbers here. So this does not align to any n which is a member of the natural numbers. Now I've chosen a particular mapping here, but the argument is general. I can always create a function. In fact, I can create a great many Cantor functions which are not in the table here. And what that then shows me is that the number of functions from n to n0 is uncountable. It's an uncountable infinity, and what that means is that we can't align them to the natural numbers, just like we can't align the real numbers to the natural numbers. There's more of them, and that's going to have some deep meaning and repercussions on the consideration of whether or not there exist non-computable functions.